Hi, we are Jack Carr and Kevin Chen, and this week we'll be discussing the internal components of a reciprocating saw, which is also commonly known as a Sawzall. A reciprocating saw is a power tool that comes both corded and uncorded to bring on the go. It is an extremely versatile tool for many job site applications. With the ability to swap out different types of saw blades, a single reciprocating saw is able to cut plastics, wood, and metals with ease. After a blade is worn out from extensive use, it can easily and affordably be swapped out with a new blade in seconds. Here is a simple overview of the interior components of a reciprocating saw. A DC motor powered by a battery or a cable turns a spiral bevel gear system as circled in orange. This gear system spins freely in place as it is held by a shaft and a closed ball bearing as circled in green. The rotary motion of the gear is converted into a linear back and forth motion through a Scotch yoke mechanism, and the tip of the shaft that exhibits this back and forth linear motion features a threaded fastener, as shown in blue, that enables a saw blade to be inserted and locked in place. The mechanical advantage from the motor of the Sawzall to the output shaft of the Sawzall relies solely on the gear ratios as seen in the spiral gear. A typical DC motor used to power a Sawzall would be a 795 DC motor that runs at about 11,000 RPM and 4 kg/cm. With a 12-tooth pinion gear on the motor shaft driving a 48-tooth bevel gear, we can calculate the gear ratio to be approximately a 4:1. Thus, an output of 16 kg/cm at 2,750 RPM would be exhibited by the output gear. This converted to a linear force enables a maximum of 4 kilograms of force to be delivered to the saw per stroke. As a preface, here's a similar Scotch yoke system that converts rotational energy into a linear motion, just like how our main spiral bevel gear converts its rotations into a linear sawing motion in a Sawzall. Here is a simplified diagram of how the inner components of a reciprocating saw works. First, a 795 DC motor rotates a pinion spiral bevel gear. This gear rotates a larger gear held in place by a ball bearing at its base. This large gear is mostly flat at its top, an exception to a single nub that enables the Scotch yoke mechanism, as you can see in the right diagram, to convert each rotation of the gear to a back and forth stroke in the output shaft. The output shaft also has a hole at its tip, which enables the insertion of a saw blade to be locked in place by a fastener set screw on its side. Here's a free body diagram of the three previously mentioned components. From the Scotch yoke mechanism, the bearing exhibits an equal and opposite force that fluctuates between -4 kilograms to 4 kilograms radial to its axis. It also experiences a moment about the z-axis because of the separation in the two acting forces as you can see in the top left. Looking at the two gears, a similar fluctuating force is exhibited on the nub of the gear and from the gear to the connecting shaft in the center of the gear. The input torque of these gears is delivered by the motor, as we've previously discussed. For the threaded fastener, we assume that the chosen saw blade has a hole in it in which the bolt can fit through. This enables a force from the blade to act perpendicular to the bolt threads. An equal and opposite force load is also applied from the shaded blade holder part to the bolt itself.
An important part of the reciprocating saw is the spiral bevel gear. These gears are used to change the plane of rotation inside the saw, and they are also used to change the motor output to essentially control the amount of force given from the motor to the saw. So you can choose what that is. A spiral bevel gear set was chosen because it's less noisy, has less vibration, and handles shock loads better than the straight counterpart without the spiral effect. Another important part of the saw are bearings. A standard unflanged 608 ZZ ball bearing is what is typically used. They handle low axial loads, 347 kg or 140 kg, An important part about these bearings is that they support 34,000 RPM, whereas the saws only go to 3,000 basically. So that enables these bearings to have essentially infinite life, and they only cost about $2 a pop. So it's a very cost efficient, stable option. Lastly, most machines need fasteners. So we're using an 8 by 20 millimeter bolt. 15 threads and 20 millimeters long will give us a very standard pitch for this kind of bolt. It's a good pick because they're very standard. They're pretty cheap, only about $4, easy to find and replace, and it provides a high tightening torque, at 8 newton meters, and a preload of 7.1 kilonewtons. So you're getting about all you can ask for. If we were to make some improvements to this saw design, one thing we could start with is adding a second bearing to hold the gear in place. The gear is only attached with one bearing, which would essentially allow a moment to be handled only by one bearing, which would be a critical element, and that's a place where you could fail or cause bending. So another bearing on the opposite side would help counteract that. Additionally, reducing the distance between the bearings and the gear will actually help also reduce that moment and potentially increase the life of the product. Thanks for listening. This has been Kevin Chen and Jack Carr with the Reciprocating Saw.